In this lecture, we discuss some examples on vector spaces. The example number 1. Check whether the singleton set V, which is equal to 0, this is a singleton set which contains only the 0 element, is a vector space under usual addition and multiplication. Its solution: the singleton set V equal to 0 satisfies all the conditions of being vector space under usual addition and multiplication. So it is a vector space. It is called trivial vector space, which contains only 0 vector or null vector. So let us take how it satisfies all the 10 properties of being vector space. So first property, if we see the closure axiom, so if we add 0 plus 0, which is equal to 0, which belongs to singleton set 0. If we go to the second property, if we use the associative property 0 plus 0 plus 0, which is equal to 0 plus 0 plus 0, which is nothing but 0. So second property also hold. If we write down the third property, which is called additive identity property. So 0 is the additive identity of 0. The fourth property is additive inverse. So 0 plus 0, which is equal to 0. So 0 is additive identity or additive inverse of itself. Now, if we go to the fifth property, fifth property is commutative property. So 0 plus 0 equal to 0 plus 0. Sixth property, scalar multiplication. So if A belongs to R and 0 belongs to singleton set 0, then A into 0, which is equal to 0, belongs to singleton set 0. So it also satisfies the scalar multiplication. Seventh property, distributive property. So distributive property means A into 0 plus 0, which is equal to A into 0 plus A into 0, which is equal to 0 plus 0 is 0. Similarly, eighth property, 0 into A plus B, which is equal to 0 into A plus 0 into B, which is also 0 plus 0. Ninth property, 0 into A into B, which is equal to 0 into A into B, which is equal to 0. And the 10th property, 1 into 0 is equal to 0. So all the 10 properties of being vector space are satisfied by the set of singleton set 0. Therefore, it is a vector space under the usual addition and multiplication. Now, the example number 2. Investigate whether the set of natural numbers n under usual addition and multiplication forms vector space or not. So the set of natural number n plus dot does not form vector space under usual addition and multiplication because it does not have additive identity 0. And we know that n contains the number 1, 2, 3, and so on. So here in this set of natural number, 0 is not present. So since it does not have identity element, therefore it will not satisfy the identity property of being vector space. Therefore, it is not a vector space. Similarly, if we consider 2 is element of n, then minus 2 is also not element of n. Is not element of n. So each and every element of natural number does not have additive inverse. So that's why the set of natural number under addition and multiplication does not satisfy all the properties of being vector space. Therefore, it is not a vector space. Let us go to the Next example, example number 3. The set of whole numbers W under usual addition and multiplication does not form the vector space. Why? Again, we have the same criteria, because since W is a number system which contains 0, 1, 2, 3, and so on. So here it satisfies the closure axiom, it satisfies the associative axiom. Since 0 is present, so it also satisfies the additive identity. But if 2 belongs to W, but uh, at the same time, -2 is not element of W. So there is no negative number of the all whole numbers. That's why it will not satisfy the additive inverse of the vector space. Since it does not satisfy all the properties of being vector space, therefore it is not a vector space. Next example, example number 4. The set of whole number W plus dot under usual addition and multiplication does not form the vector space because it does not satisfy additive inverse property, that is for any whole number V in W minus V is not in W. The fourth example, the set of integer is not a vector space under usual addition and multiplication. Why? So if we write down the set of integer, we have -3, -2, -1, 0, 1, 2, 3. So now all negative number, all positive number, including 0. If we check that this will satisfy all the properties of vector space or not. So first property hold, closure axiom hold, associative axiom hold, additive identity is 0. And for each and every element, their inverse is also present. So additive inverse also property also exists. Commutative property also hold. But if we go to the sixth property, scalar multiplication. Scalar multiplication. So now let us take, if 2 is element of Z and 1 by 3 is element of R, and if you multiply 2 into 1 by 3, which is equal to 2 by 3, which is not element of integer. Therefore, the set of integer is not a vector space because it will not satisfy the sixth property, scalar multiplication. The set of integers Z plus dot is not a vector space under usual addition and multiplication because it does not satisfy the closure axiom for scalar multiplication of integer with real number. Example number 5. The set of rational number q plus dot is not a vector space under usual addition and multiplication. Why? The same situation comes over here. Let us take 1 by 2 is element of q and √3 is element of r. And if you multiply this, √3 upon 2, which is element of r, but it is not element of q. So therefore, it does not satisfy the closure axiom for scalar multiplication with the real number. Therefore, this is not a vector space under usual addition and scalar multiplication. Example number 6. The set of irrational number q dash plus dot is not a vector space under usual addition and multiplication. Why? Now here, if we take two irrational number, let me take 2 plus √3 and 2 minus √3. These are two irrational number. If we add these two irrational number, 2 plus √3 plus 2 minus √3, the answer is equal to 4, which is rational number, not irrational number. So addition of two irrational number need not be necessary that it will be irrational number. So therefore, it does not satisfy the closure axiom. Hence, the set of irrational number q dash plus dot is not a vector space under usual addition and multiplication because it does not satisfy the closure axiom for vector addition. So these are some fundamental examples of vector space or not a vector space. In the next lecture, we discuss about some more examples of the vector space. Thank you.